We are privileged to have Dr. Prabha Mandayam, who's an associate professor at IIT Madras, joining us today. The title of her talk is Noise Adapted Quantum Error Correction and Fault Tolerance. So just a few things about Prabha. So Prabha is an associate professor. She obtained her PhD in physics from Institute for Quantum Information and Matter at Caltech. After a postdoc fellowship with the Optics and Quantum Information Group at the Institute of Mathematical Sciences, and a brief stint as Inspire faculty fellow at Chennai Mathematical Institute, she joined IIT Madras in 2014. Her research interests are in the area of quantum computing and quantum information theory. In particular, she's interested in quantum error correction, understanding the interplay between quantum foundations and quantum cryptography, and using quantum information as a tool to explore fundamental questions in theoretical physics. So before I hand over the mic to Prabha, just a few things for the audience. So please turn off your video and please keep yourself muted unless you have a question, and then you can use the raise hand button, and then I will call on you for the question. Okay, Prabha, please go ahead.
Thank you. Thank you, Akshay, for the wonderful introduction. And thanks to the team at IQTI for inviting me to one of your seminar series and having me give a talk here. So I'm just going to, I suppose that you can see my screen in full now?
Yes, yes.
Okay, great. All right. So as Akshay mentioned, my primary research interest is on quantum error correction, and that's the mandate I was given today to talk about some recent work on noise-adapted quantum error correction and fault tolerance. So I was also told to spend some amount, like make it a colloquium style talk, so have some amount of it devoted to introduction and at least introduce all the basic tools and concepts that we will need. So I will start by talking about decoherence and quantum channels. I will make a distinction between general purpose quantum error correction and channel adapted quantum error correction, and that will lead directly into the kind of research that I'm doing, which is about what is an efficient or optimal way to do quantum error correction in today's era of noisy intermediate scale quantum devices. So I will talk about the problem of noise-adapted QEC, the problem of finding good quantum codes for specific noise models. And this is an earlier piece of work. I will just mention this in passing. I may not discuss this in detail. But what I would like to really talk about then in the later part of the talk is fault tolerance. And I would like to talk about how this so-called channel-adapted or noise-adapted codes can also be used to build fault-tolerant quantum circuits. Okay, so that's the final point is a bit of detail, which we'll see if we get that far, then that's a bit of a technical detail. But what I would like to present basically is this idea of noise-adapted error correction and how that can also potentially lead to making fault-tolerant quantum circuits. Okay, so yes, we all, yeah?
Yeah, fast through automation.
Is there a question?
Actually, simple step. First,
Okay, can people mute themselves? Sorry about that. Let me.
Okay, yeah, that's fine. So maybe I'll just continue. Yeah, at some point in the middle, I will have a natural stopping point where people can ask questions. But in between, if you have any pressing questions, please feel free to type in the chat window and I can address them as and when. Okay, so we all know today that we are looking at companies with hundreds of qubits, devices with hundreds of qubits. These are what are typically called noisy intermediate scale quantum devices. We'll see why this name, right? Because first of all, we're still counting qubits, right? We're saying that Google's Sycamore processor has 72 qubits, IBM's Falcon processor has 120 qubits, and so on and so forth. So there seems to be some challenge in scaling up these number of qubits, right? That seems to be one issue. And the second seems to be, for those of us who have maybe run some tasks on these processors, we know that these qubits and these processors are fairly noisy, right? So hence this term that, of being in a noisy intermediate scale quantum era. So noise, not just in the quantum bits, but also in the quantum gates, poses a serious challenge to translating the promise of quantum computing or the potential of quantum computing into a practical reality today, right? And one, maybe as of now, perhaps the only way that we know of overcoming this challenge is to use what is called quantum error correction, right? And this provides us some basis to thinking that these quantum devices that we see today with maybe 50 or 100 qubits can indeed be scaled to become robust universal quantum computers, right? And that's what we're going to look into today a little bit. What is quantum error correction? But before that, what is this noise? How do we model noise? And then how do we correct for it? So what is noise? Well, noise is an inevitable quantum phenomenon. It basically happens because quantum bits, quantum states don't live in isolation, right? I guess you can see my pointer here. I didn't check that earlier whether you could see my pointer, but Akshay, can you just confirm you can see my pointer?
Yeah. I can see the mouse.
Thanks.
Yes.
All right, thanks. So this is what I call the system Hilbert space. This is the system of interest to us. This could be our superconducting qubit. This could be our ion trap qubit. It could be a photonic qubit. This system does not live in isolation. It undergoes unavoidable interaction with its environment, which I call heads up E, the Hilbert space of the environment. And of course, we know that the system plus the environment of the reservoir can be treated as an isolated system. So jointly, they undergo unitary evolution, right? Via some unitary which comes from the joint system Bath Hamiltonian, right? But if I'm interested in looking at the dynamics of the system alone, in this scenario, where it's no longer a closed quantum system, but an open quantum system, then we realize that this evolution, I've called this input and output, but you can think of this as the state at time t0 and the state at a later time t1. This evolution, this arrow out here, is not a unitary evolution because you have to trace out the degrees of freedom of the environment over which you don't have control and simply look at system evolution. And when we do that, we realize that that's no longer unitary. So what happens is the system could start in a pure state and end up with something which is a mixed state. And this is what we call loss of coherence because this can never happen under a unitary transformation, right? A unitary evolution would preserve purity, but typically system states alone undergo what is called decoherence, which is loss of coherence because of this interaction with the environment or the bath. And this is what we call noise. And this evolution gets modeled as what is called a quantum noise channel. So as I said, this evolution is not unitary. So what is it, right? Mathematically, this is modeled as what is called a completely positive trace preserving map. Let's not maybe get into the details of what that is, but maybe this expression is not so hard to understand. We have a system state out here, and I have a state of the environment. I assume that they start out in a product state initially. That's what I have here. And then they undergo this unitary evolution under this joint system environment unitary. But I now want to understand what happened to the system state alone, so I trace out the degrees of freedom of the environment. And what I end up with is a map that acts purely on the system Hilbert space, which has this mathematical property that it's completely positive and trace preserving. So such maps can actually be described somewhat nicely by a set of so-called Krauss operators. Okay, so the transformation of the state can be written as this map acting on the system state. This map can be realized simply by the action of this sum of operators acting on the system state. And this set of operators has to satisfy some normalization condition in order to make this a trace preserving map. Was there a question?
No.
Okay, yeah, I heard some noise. So here's a simple example of what one means by this. So I have a two-level atom here. My one can think of a superconducting qubit, for example, as an artificially prepared two-level atom like this, where my system essentially effectively has access to these two levels, a ground state and an excited state, but it of course interacts with the modes of this cavity that it is sitting in. And via this interaction, the excited state can of course decay to the ground state in a spontaneous fashion, leading to the emission of a photon, right? This kind of an interaction is famously modeled by the so-called Jaynes-Cummings Hamiltonian. And under certain restrictions and assumptions, one can do exactly what I just described. You take the Jaynes-Cummings Hamiltonian, you work out the unitary interaction between this two-level atom and the bath. You trace out the degrees of freedom of the bath and look at what happens to system states alone. Now, the system is a two-level system. So there's a ket 0, which is going to be my ground state. There's a ket 1, which is the excited state. So I'm going to represent this process as basically the action of these two operators, okay? So there's going to be an E0 operator, which, as you can see, preserves the 0 state. It does nothing to the 0 state. It damps the 1 state a little bit. It damps it by a factor 1 minus gamma. And if you look at the second operator, this is actually the operator which models the dissipation from the excited state to the ground state. It takes a ket 1 and brings it to a ket 0, and this happens with a prefactor gamma. So this gamma out here represents for me the probability that the system will decay from the excited state to the ground state with the emission of a photon. And what this factor of 1 minus gamma here tells me is that if I do not observe, if I or the cavity do not observe this photon coming out, then I know that the one state has not decayed into the ground state, right? And that is why this damping factor sits here of 1 minus gamma, right? So it's basically a probability conservation. And this process of a two-level system undergoing dissipation by interacting with the cavity modes is what gives rise to one of the most ubiquitous noise channels in quantum computing, namely the amplitude damping channel. This is a very natural process that occurs naturally in several qubit architectures, basically superconducting qubits, ion traps, etc. This is also often called a T1 process in the language of open systems. T1 modeling what is called the coherence time of this two-level system. It denotes the time scale at which this decay or this dissipation is happening. And of course, you see that if I start with a pure state, namely a ket 1, I don't end up with a pure state because with some probability, I have undergone this decay process to ket 0. And with some probability, I remain in a ket 1. So what I end up with is a mixture, an incoherent mixture of a ket 0 and a ket 1, although I started with a pure state, namely the system being in the excited state. So this is a simple example of decoherence. What generally goes by the name of decoherence, although here you'll realize that what's happening is actually damping or energy dissipation. So the name that we will give for these kind of processes is quantum noise or quantum channels more generally. So here's an example of what these coherence times look like. So I just put this in here to indicate what the kind of coherence times that today's superconducting qubits have. This is from already a year ago. But I don't think this has changed very much. You see that the lifetimes of these qubits, when you say lifetime, you see what they're plotting is basically T1 times. The red dots are all the T1 times. The blue dots are what are called T2 times, which is associated with a different kind of quantum channel, namely dephasing rather than damping, right? And these lifetimes you see are somewhere around 100 microseconds, right? Which means that if I wait beyond 100 microseconds, then the state of my qubit has completely decohered into a mixed state, right? So the point is that if now I want to think of this qubit as my basic building block of a quantum computer and I'm going to start doing operations on it, you realize that this qubit does not live long enough for us to do sufficient number of gate operations, right? So this today is one of the biggest challenges in scaling up these building blocks into full-blown quantum processors. So I just want to now get a little bit into this noise models and talk about error correction. And rather than talk about the model that I described, which is a very physical model, which comes from two-level atom interacting with its field and so on, I want to talk about maybe a slightly artificial model, which is motivated from the classical literature, right? So this is what is called a bit flip channel. Classically, bits 0 and 1, this is probably the biggest source of noise, right? The bit can flip, a 0 can get flipped to a 1 and a 1 can get flipped to a 0. Quantumly, this is what it looks like. I have a ket 0 which can flip to a ket 1 and a ket 1 which can flip to a ket 0. But this may not be a natural noise model for the architectures, but this is a very, this has a very nice structure to it mathematically. It is symmetric, first of all, between 0 and 1. And the reason it has a very nice structure is because I can think of this noise as arising because of the action of a certain Pauli operator, namely the sigma x operator. So it's as if with probability p, the sigma x acted on the qubit, and with probability 1 minus p, the qubit was left unchanged. And this again is an example of how I may start with a ket 0, but then I end up decohering into a mixed state of this form, 1 minus p00 plus p11. And in this case, the Krauss operators are simply identity and a Pauli operator, namely sigma x. And once again, I have sitting here this error probability, which is a function of time, similar to the gamma that I mentioned, and there's a time scale, which is the coherence time. I can then also do the same thing and talk about a sigma z noise model, right? That is what we would call a phase flip channel, where instead of identity and sigma x, I now have identity and sigma z occurring with some probabilities. In that case, rather than 0 and 1, it may be more convenient to think about plus and minus, and you can see that the plus would get flipped to a minus with a certain probability and vice versa. So this class of noise models is what we generally call Pauli noise channels. Why? Because the operators that represent the action of the noise, namely these so-called Krauss operators, are essentially just Pauli operators, right? So I can then put all the three Pauli operators that act on a single qubit together and construct a noise channel called the depolarizing channel, where either of the three Paulis could have occurred with the same probability, which is p over 4, and the qubit was left unchanged with the probability 1 minus 3p over 4. And this is what is called the depolarizing channel, right? So the difference between the classical and the quantum case, one already starts to see the difference between noise affecting classical bits versus noise affecting quantum bits. Classically, bits can get flipped or get erased. And that pretty much covers the entire gamut of noise models I can think about. But quantumly, bits can undergo, qubits can undergo a noise of the bit flip form. They can undergo noise of the phase flip form. They could undergo depolarizing noise, or what may be much worse, they could undergo amplitude damping. And if you think about it, amplitude damping does not really have the structure of any of the Pauli operators. It cannot be written simply as some scalar times a Pauli operator, right? So this kind of a noise model, which is where my primary interest lies, is what I will call a non-Pauli channel, okay? But to understand quantum error correction, maybe it's useful to simply start with a bit flip channel and then build up our intuition from there on and see if that works for non-Pauli channels, right? So I'm going to talk now about quantum error correction. Maybe I can take a question or two if there is any at this point. Akshay, do you see any questions or any raised hands?
Yeah. Vyom, please go ahead with your question. Unmute yourself and ask the question.
Okay. Hi. In the Jaynes-Cummings model, the Krauss operators that you have shown, they only take the one state to the 0 state with some probability. But like in the Jaynes-Cummings system, the Hamiltonian is a combined resonator and the two-level system, right? So it is possible that if when the when the one state goes to the 0 state, the photon that is emitted is in the mode of the resonator. In that case, that is not a decoherence process, right? It's a coherent process. But the Krauss operators are not taking care of that.
It's a Krauss operator if you think of the, if it's a coherent process, we think of the combined system.
Right.
Right? But
right.
I don't my information is not stored really in the resonator modes, it's stored in the two-level system, right?
Okay.
It's
Right.
really stored in the two-level system. So as far as the two-level system is concerned, it's not a coherent evolution. It's not a unitary evolution. Because of this fact that I've had to trace out the cavity modes or the resonator modes, right? So
Okay.
it's
Okay.
like this example that I gave you, that if I started with a ket1, so if you were to think about it as a coherent process, you have to start with a joint state of this two-level atom and the field. On such joint states, it is unitary, it is coherent, coherence is preserved. But once I trace out the cavity modes, and I just look at this ket0 and ket1, it is no longer unitary. Okay, does that answer your question? Yeah.
Yeah, thank you.
Sure. Okay, so moving on. Right, so this is just a nice limerick which captures the essence of what we are trying to do with quantum error correction. This is due to Daniel Gottesman from almost 30 years ago. It says, with group and eigenstate, we've learned to fix your quantum errors with our quantum tricks. So we now know what quantum errors are to some extent. So what are these quantum tricks? And why is he talking about group and eigenstate? Okay, so the quantum trick that we are going to do is to encode a single qubit into 3 qubits. Okay, this process is what is called encoding. I'm going from a single qubit system, and that same information that exists in the single qubit system, I'm going to now put it into a 3 qubit system via preferably an isometric process, right? So more precisely, this is what I aim to do. I take alpha 0 plus beta 1 and I map it to alpha 0, 0, 0 plus beta 1, 1, 1. So why is it this kind of a mapping? So first of all, we realize that quantum information cannot be simply copied. The no cloning theorem tells us that I cannot copy arbitrary quantum states. But the whole idea of error correction is to somehow be able to preserve arbitrary quantum states without knowledge of what that initial state is. Because the minute I try to get knowledge, so I start with something like alpha 0 beta 1, I cannot simply make 3 copies as if it were a classical repetition code. So I need to find an encoding process which does exactly this, where that information is now stored in an entangled state of the 3 qubit system. You realize that, for example, if alpha and beta are 1 over root 2, then this is a GHZ state. So this has to happen via a unitary process. And I say unitary because I also need the ability to decode if I encode, right? So this process has to happen unitarily, and it has to circumvent the no cloning theorem, and it has to happen in a way that doesn't end up with me measuring or destroying the superposition in the initial state. So here's a circuit that shows how this can happen. So this is a complete circuit for the 3 qubit error correcting code. As you can see, it's a very neat and simple circuit. I have the state that I wish to protect. That's my ket psi here. I have 2 additional ket zeros. These are what I call ancillary qubits. And this is one resource requirement that I need for error correction, because I need to protect my information via redundancy. And the way I introduce redundancy is by adding additional systems. And so I initialize these additional systems to some ket 0, and then I perform appropriate unitary operations that can entangle my initial qubit with these 2 ancillary qubits, so that my information is no longer residing in just psi, but it's actually residing in an entangled state of this 3 qubit system. And you realize that this simple circuit with 2 C naughts will achieve exactly this encoding that I want. Now, how does the error correction proceed from there on? What has this encoding gained me? What this encoding gains me is that, suppose now I have a single qubit bit flipped error, right? Which means that maybe the first qubit got flipped. So this alpha 0, 0, 0 plus beta 1, 1, 1 becomes an alpha 1, 0, 0 plus beta 0, 1, 1. You realize that the single X error maps this encoded state into an orthogonal 3 qubit state. So this encoding itself makes use of just a 2-dimensional subspace of the 3 qubit space. The 3 qubit space is a big one. It's an 8-dimensional space. And I'm just making use of a two-dimensional subspace of this 8-qubit space. And individual errors act in such a way, in this case, we are correcting for bit flips, right? So the individual bit flips act in such a way that they map this two-dimensional subspace into orthogonal subspaces of the larger space. I have a picture for this in the next slide, which I will just show you. Sorry, not here, maybe, yeah. So this is the kind of picture that I have in mind. I have my code space. The C out here is what I call a code space. That's a space which has the encoded states, the alpha 00 and the beta 111. And E1 could be a bit flip on the first qubit, E2 could be a bit flip on the second qubit, E3 could be a bit flip on the third qubit, and so on. These different errors, I encode in such a way that these different errors map this encoded state into orthogonal states, or states living in non-overlapping subspaces of the 3-qubit space. So let me go back to this example now. So what have we done? We have gone from physical qubits to so-called logical qubits. We've gone from a single ket 0 to this logical 0, which is 3 ket zeros. We've gone from a single ket 1 to the logical 1, which is 3 ket 1s. So a single alpha 0 plus beta 1 becomes this. And then the action of the noise is such that the action of the different single qubit errors is actually distinguishable via a measurement. So the second part of this circuit out here does precisely that. It tries to measure and identify where the errors occurred. But where is the measurement happening? Well, the measurement is actually happening on these two bottom qubits out here, which are two additional ancillar qubits. Why are we measuring the ancillar qubits? Well, we don't want to measure these 3 qubits where the information is encoded, because that again defeats the purpose. I want to be able to extract a signature of the error, what we often call a syndrome. So I want to extract the syndrome down to one of these ancillary qubits and measure them rather than measure the qubits, rather than measure the so-called data qubits. Okay, so that's what these C naughts are doing. There's 2 C naughts that go from the first and second data qubit to one ancillar. There is 2 C naughts which go from the first and third data qubit to the other ancillar. And what this set of 4 C naughts ends up doing is it translates or maps the different errors that can occur to different possible combinations of 0 and 1 in the ancillar. In other words, it maps the errors to the parity of the ancillar qubits. And then by simply measuring the ancillar qubits in the 0-1 basis, I know what errors occurred, and then I go back. So these two lines denote classical conditioning, right? These 2 lines indicate that whatever output I have here is a classical bit, which I then use to correct. Because this pair of classical bits will tell me which error occurred where. And based on that information, I simply have to perform an X, in this case, just an X operation. It's a unitary operation on one of these 3 qubits. So this is roughly how an error correcting code works. One of the standard 3-qubit error correcting codes works. So just to emphasize this couple of points, the bit flip on different qubits are distinguishable. That's the reason why we picked this particular encoding, so that the errors can be detected and hence corrected. And well, I only talked about the single qubit errors, because once I start bringing in 2-qubit errors into this mix, then I violate the principle of errors on different qubits being distinguishable, because some 2-qubit errors can present the same syndrome as some single qubit errors. So that puts a bound on this P, where if you recall, P was the error probability of a single qubit error. So in all this, what I did not say until now explicitly is we've assumed that the noise acts identically on each qubit and acts independently on each qubit. So this is what we call IID noise. And in this IID noise setting, we are assuming that the single qubit errors are much more probable than 2-qubit errors, which are much more probable than a 3-qubit error, and so on. Right? So this code works. It achieves this protection. It improves the coherence time of the qubit, provided this error probability of a single qubit is less than a half. Okay, so let me now formally state this idea of error correction in more formal mathematical language. So we encode information from the physical space, which was maybe a d0 dimensional space. In our case, it will usually just be a qubit, into a d0 dimensional subspace of a larger Hilbert space. Okay, so we started out with a qubit. We encoded it into a two-dimensional subspace of a larger space. In that case, it was a 3-qubit space. And this two-dimensional subspace gets a special name. It's what we call a code space. This is where the information that we wish to protect resides. This encoding operation is done unitarily. That's the circuit that I showed you. It just had 2 C-naughts, for example. And then there is a recovery map, right? And I did not really talk about a recovery map in this case because here it was fairly straightforward as to what we should do. We should put in 2 additional ancillar qubits, extract the syndrome out, measure the ancillars, and hence correct the qubit. Now, this entire process of unitary action between this encoded qubits and ancilla, followed by measurement of the ancilla, can be modeled again as one of those CPTP maps that we spoke about in the first slide. So just like how the noise could be an arbitrary quantum map, which is a completely positive trace preserving map, similarly, this entire recovery process can be abstracted as a completely positive trace preserving map. It's a map that acts now from the larger Hilbert space into which the system is encoded, right? It acts on this larger Hilbert space on which the system is encoded and brings the information back to the code space. It brings the information back down to that two-dimensional subspace of this larger space. Okay, so now whatever I have described is what we would call perfect error correction. We say that the action of a channel is perfectly correctable on some code space if every state in the code space can be recovered after the action of the channel meaning the noise, and the recovery. And for a perfectly correctable code, we require this picture to hold, which is that distinct errors must map the code space into non-overlapping parts of your larger Hilbert space. Then one can formally show that you can construct a recovery map which will distinguish between all these different errors and allow you to trace back to the code space. Okay. Of course, this requires additional qubits. It requires you to act on a larger space and so on. But one can write down an algebraic condition which tells you that this is possible. Okay. But now this is an idealization, right? That every state in the code space is going to be preserved exactly after the action of the recovery. This is an idealization. This picture is also an idealization because for every noise model, it may not be the case that you always have a code space, that you always find the code space, which is going to map the code space to non-overlapping spaces, right? So instead, what you may have is a more distorted picture like this. In fact, you could have a more general picture where some of these distorted cuboids could actually be overlapping, right? So this kind of a picture is what may be more natural, and this is what we call an approximate code. So we say that a noise is approximately correctable if there exists a recovery channel. Here, the quantum channel R always represents for me a recovery channel, such that every state row in the code space, so this is just notation to say that this is a state on the code space. This row belongs to the set of states on the code space. So for every state in the code space, I can find a recovery map such that after the action of the noise and the recovery, I don't end up with exactly the same state, but I end up with something which is approximately close to the initial state. And this seems like a much more realistic scenario, and this is what goes by the name of approximate quantum error correction, right? And this is what we would like to study in a bit more detail, right? So before I get into that, let me also motivate the need to look into or the need to say move away from perfect error correction, right? So as I mentioned earlier, in the quantum case, we have a continuum of different errors that can occur on a single qubit. You can have erasure, you can have phase flip, bit flip, amplitude damping, depolarizing, etc. Now, this what we outlined earlier, which was the 3-qubit bit flip code, it encapsulates the idea that you correct for one of these Pauli noise models, right? So you can sort of extend that idea now. You can take the 3-qubit code and you can add more qubits. You can make it a 9-qubit code, let's say. And then you can show that you can correct not just for sigma x errors, but you can also correct for sigma z errors. So the philosophy of general purpose error correction says, well, we know or we are able to figure out how to deal with Pauli errors. For example, figuring out how to deal with bit flip was not so hard. Similarly, I can imagine that by rotating the bases, I essentially have a code for phase flip. Then I can put these two codes together and I get a code that can correct for both bit flip and phase flip. How does that help me? It helps me because the Pauli errors form a basis. They form a basis for the set of all possible single qubit operations. So any error on a single qubit should be representable as a linear combination of the Paulis. In fact, the damping errors that I wrote down on my second slide can also be expanded as a linear combination of the Pauli operators. As I said, they cannot be written simply as a scalar times a Pauli, but they can be expanded as sigma x plus I sigma y or I plus something sigma z and so on. So if I'm able to correct for the Pauli error basis, and if I have a linear theory of error correction, then I can correct for arbitrary single qubit errors. And this is where we had the first line of Gottesman's limerick, that with group and eigenstate, we've learned to fix quantum errors. Because these Pauli operators come with a nice group structure, which then leads to the so-called stabilizer codes. And we have a very nice theory of general purpose quantum error correction that comes from this, right? Now, it turns out that if one were to view all errors in the Pauli basis, then you can put a bound on what is the shortest quantum error correcting code that you need. And the shortest such code requires 5 qubits to protect a single qubit code. This is a so-called quantum Hamming bound. However, so this, for example, now you can try to ask, well, I start with a non-Pauli noise model, like amplitude damping, and then I look at how well does my 5-qubit code do for this non-Pauli noise. So one can theoretically estimate that this 5-qubit code achieves some fidelity, and I'll just explain to you very soon what I mean by fidelity, but it's just a parameter which tells you how well the code does. Now it turns out that one can actually write down a 4-qubit code, which is a shorter code, okay? One can write down a 4-qubit code, which is a shorter code, which can actually perform the same error correction, which can achieve a similar fidelity with just 4 qubits. So in a way, this 4-qubit code is actually 4-qubit code is like, and this ties in with what I said earlier about approximate error correction also, because now what I'm going to tell you is that this 4-qubit code is not a perfect error correcting code. It comes under this class of approximate error correcting codes, and it is tailor-made or adapted to correct for single qubit amplitude damping errors. So this is what the 0 logical and the 1 logical look like for the 4-qubit code. The 0 logical has a somewhat similar structure to the 3-qubit repetition code state that we wrote down, but the 1 logical looks a bit different, as you can see. So this kind of a code, firstly, it's tailor-made for amplitude damping errors, right? In the sense that this pair of code words maps me to a 2-dimensional subspace of the 4-qubit space, where I can actually distinguish between all the single qubit amplitude damping errors. But as per the Hamming bound, this cannot be a perfect error correcting code for Pauli noise, but rather it's a tailor-made error correcting code for single qubit amplitude damping errors. And here's a simple isometry circuit that can achieve this encoding. And it's not very much more complicated than the 3-qubit encoding circuit. And as before, it circumvents the no-cloning theorem using ancillas and entangling unitaries. And single damping errors on different qubits become distinguishable. So if you recall our amplitude damping channel, the probability of a single damping error was order gamma. So effectively, what we are doing is we are able to correct for errors up to order gamma squared onwards, which are the 2-qubit errors. We do not really correct for them, which is in a sense similar to the 3-qubit repetition code for the bit flip errors. And this goes back to what this fidelity expression here tells me. It says that I have something, the sort of leading order deviation from 1 in fidelity is order gamma squared, right? And the 4-qubit code achieves a similar sort of fidelity function in terms of gamma. So this brings us to the idea of noise adapted QEC. That is it then possible to develop efficient quantum error correcting schemes for specific noise models and specific qubit architectures? So once again, like in the case of the bit flip code, this code improves the coherence time of the qubit, provided this gamma, the probability of decay of the qubit, is less than a half, right? So what is this fidelity function that I've been talking about? So let me just quickly define this function. I've already said all of this, but this expression out here is what captures what fidelity is, okay? So it basically compares the initial state of the qubit, which is the ket psi and the bra psi here, with the final state of the qubit, the final state after the action of noise and recovery. So I take the overlap of the final state after the action of noise and recovery with the initial state. That itself is a metric. That's a fidelity metric. It's often called the Bio's distance. It's related to the Bio's distance via a square root. But what I'm typically interested in is not about the performance of a single state. I want to be able to protect arbitrary states in the code space. I could either do this by averaging over all states in the code space, but that would only give me an average estimate of the fidelity. That will not tell me that even in the worst case, I'm guaranteed a certain degree of fidelity. In order to have that guarantee, I need to look at a function called the worst case fidelity. And that is what this equation defines for me. It's a minimization over all states in the code space of this fidelity function. Okay, and this is what we call the worst case fidelity. And for amplitude damping noise, if I had a single qubit without any encoding, without any error correction, then one can theoretically work out that this fidelity falls off as 1 minus gamma. Whereas if I had a 4-qubit code, then this fidelity would fall off as 1 minus something times gamma squared. So 1 minus something order gamma squared, just like how I had this for the 5-qubit code. Here it was 2.5 gamma squared and there is 2.75 gamma squared. So you actually see that as far as the amplitude damping noise is concerned, the 4-qubit code achieves comparable fidelity to the 5-qubit code, and you actually gain in terms of resource in the sense that your data qubits now only have 4 qubits and not 5, right? So I then want to now talk about my own research a little bit on noise adapted quantum error correction. Firstly, this was just one example of a noise adapted code. So can we then, how do we systematically construct such noise adapted codes? And also, what is the optimal recovery map to use for these kind of noise adapted codes? So before I get into that, if there are any questions at this point?
Kanath, please go ahead.
Ma'am, is there any physical setting where we can encode this qubit in a higher dimensional Hilbert space? I mean, example of physical experimentally.
By higher dimension, so that is what this circuit does for me, right? So for example, this 3-qubit circuit does precisely that, right? So you want to know if this has been experimentally implemented, then yes. You are also welcome to go run this, for example, on one of IBM's 5-qubit processors. You can do this encoding. So in this case, the higher dimensional Hilbert space is simply a tensor product of qubit spaces. So my qubit is 2-dimensional. I take C2, by which I mean complex Hilbert space of 2 dimensions. I take C2 tensor C2 tensor C2. That is my 8-dimensional space. But if you're asking me whether you want to, do you want to encode a qubit in some D-dimensional space where D is not necessarily just a tensor product of qubit spaces. Was that your question? Or
No,
was
I
it
just
just
wanted
this?
the
Yeah.
experimental realization.
Yeah, so this indeed has been implemented. It has been implemented in NMR. It has been implemented in superconducting qubits. Yeah, it's pretty much the 3-qubit kind of code has been implemented in almost all architectures. The 7-qubit code has been implemented. The 9-qubit code has been implemented, right? So we have proof of principle of these implementations of these error correcting codes. Okay.
Okay, thank you, ma'am.
Yeah, I used to have a slide at the end where I listed some references. If I have that, I'll pull that up at the end. Okay.
Okay.
Yeah.
Okay, Prabha, just think you have about 15 minutes.
Okay, perfect. Yeah,
Okay,
yeah.
thanks.
So I think I've laid out the ground, but yeah, let's see how far we can go in terms of the my own research. But that's okay. I think yeah, I'll wrap up in 15 minutes. That's fine. Thanks. Okay, so hopefully I've motivated the need for noise adapted or channel adapted error correction. So let me briefly tell you about some of our contributions here. So one of our early contributions was to study this question of optimal channel adapted recovery map. Okay, so this particular example was amplitude damping noise, right? But given any arbitrary noise model, is there a way to construct a recovery that is adapted to that noise? And is there a way to do this in an optimal fashion? So in one of our early works, we showed that there exists something which is today called a PETS recovery map. There is a way to construct from the noise operators themselves, the operators of the recovery map. So if you recall, this EI were the noise operators, the Krauss operators of the noise. From that, I can construct an RI, okay, a set RI, which models for me which basically represents for me the Krauss operators of the recovery map. And hence, I can construct specific to a particular noise and a particular code. I can always construct this recovery map. And we showed that this is indeed a near optimal recovery map, which means if there were a good recovery map for this noise and this code, then our recovery map, namely the SPEDS recovery map, will achieve a fidelity which is very close to that of the optimal map. So now, given a noise and a code, you don't need to go searching over all possible recovery maps, but you can actually simply work with the PEDS map, this particular construction of the recovery map, because this will achieve as good of or close to optimal fidelity. Okay. So optimal recovery channel for any pair. Now, this turns out to be a very useful theoretical tool, because what I can next do, and which is what we did subsequently, is to use this PEDS map to find good quantum codes, good channel adapted quantum codes. So I should note here that this problem of finding a good code and a good recovery, in short, finding a good error correction scheme for a particular noise, this is a triple optimization problem, if I were to write it out abstractly, right? Why? Because I'm given the noise. Okay, let's assume that we characterize the noise in the system so we know what the noise channel is. But then for that noise, I need to go ahead and find the optimal encoding. I need to find the optimal recovery map where I need to optimize this fidelity function. And this fidelity function is not a nice convex function. So it is a triple optimization problem because you have to optimize over the encoding, you have to optimize over the recovery. And what is more, if I want to guarantee worst case protection, then I have to optimize over all states in the code space. So our work basically breaks down this optimization problem into two steps. First of all, we say that we have a theoretical solution for the optimal recovery map, and that is this PEDS recovery map, right? So now I can go ahead and fix my recovery as the PEDS recovery map, and then I simply have to do a double optimization over all possible encodings and all possible states in the code space. And what we recently showed with a student and other collaborators is that one can develop an efficient, I'm sorry about this typo, one can develop an efficient numerical procedure for finding good quantum codes using a nice algebraic trick called the Cartan decomposition. Okay, so I'll refer you to this paper to see that. Yeah, so I'll refer you to this reference here because I'm not going to talk about this, but I just want to show that this problem of channel adapted error correction has a rich analytical challenge, right? And some of it is now solved using the PEDS map. And then the part about finding good codes is solved if you then parameterize this encoding unitary in terms of the Cartan decomposition. So I just want to show you some examples of how these codes work, right? So what I've plotted here is the worst case fidelity on the y-axis as a function of the damping parameter. Once again, I'm focusing on amplitude damping noise as a use case because that's a kind of classic non-Pauli noise model for me. And this red line out here is the linear fall in fidelity if I have the bare unencoded qubit. These lines out here are how the fidelity behave or how they fall for different error correction schemes. This blue dotted line out here is for the 4-qubit code that I showed you earlier, which is again a particular solution of a good error correcting code for this noise model. But now if I were to do numerical optimization, I actually end up with this pink line out here, the pink and the black. Both of these are the result of numerical search, and structured and unstructured is just some detail of how the search is done. But this basically tells you that one can do numerical search over the encoding space using this Cartan decomposition that I was mentioning and find good error correcting codes which can maybe even beat the example of the 4-qubit code that we have. They also in fact beat the 5-qubit code. The thick blue line out here is the 5-qubit code, the so-called perfect code. So we can, using our numerical optimization, find shorter codes which actually perform as well as or maybe marginally better than some of the well-known stabilizer codes. Okay, we compare with the 5-qubit because that's the closest in terms of the resource that is being consumed. Okay, I also want to show you how these error correcting codes can actually be implemented on an actual processor, right? So this is from the IBM Qiskit simulator, where what we have implemented is the 4-qubit code along with this noise adapted recovery, the so-called PEDS recovery map. And this is recent work with a couple of students, where what we are trying to do is take this noise adapted recovery map and get a circuit out of it. Because this map is an abstract thing that I'm telling you about, right? It's some set of operators. Now I need to translate that into a quantum circuit if I want to present for you a nice compact circuit like what I have for the 3-qubit error correction scheme. So what we have done here is exactly that. We take the 4-qubit code, we assume amplitude damping noise, and we construct this channel adapted recovery circuit for this case. And again, what you have out here, now I'm plotting the fidelity for a fixed gamma. My gamma has been assumed to be 0.2, which is not very low actually, right? It's assuming a fair degree of noise, okay? And even so, our circuits can actually achieve a fidelity of around 0.95 for various single qubit states. So what is on the x-axis now is theta, which parameterizes my single qubit state. Okay, so this tells me that I sweep through my theta to get, that I sweep through a certain, basically the xy, well, yeah, I basically sweep through a particular plane of the block sphere. I don't put in the phase, but I can achieve a fidelity of 0.95, whereas the unencoded qubit falls off. The unencoded qubit, you notice, achieves fidelity 1 for 0, which is ket 0. Because for this noise model, ket 0 is a fixed state. It's an invariant state. So that's left unaffected. So of course, the fidelity is 1 for that. And the ket 1 is the state that is the most damaged, right? So that is the state which has the lowest fidelity out here of 0.8. But the error corrected qubit achieves pretty high fidelity for almost all values of theta. So this is a kind of translation of whatever we've done so far with the analytical results into the circuit domain, okay? But then that brings me to another question. What I've done out here is on the simulator, okay? And this is a noiseless simulator. So now comes the real question of fault tolerance. So the circuits that I showed you earlier for the 3-qubit code or the 4-qubit code, and this performance plot that I'm showing you, although it's simulated on a quantum device, these are all assuming noiseless gates. It's assuming that somehow I do my encoding and then I turn on the noise. So in this case, the way I actually turn on the noise is in two ways. That's what these two different plots are. In one case, I'm implementing the noise via a sequence of identity gates, which means I'm talking about a qubit that is idling, that is sitting still while maybe other qubits undergo computational gates and so on. It's a very natural scenario in a quantum computer, right? The other way of introducing noise is to actually implement the noise via a circuit. So we do both of these here. But this is artificial because this is assuming that the encoding is noiseless and then the noise gets injected and then I do my recovery or my decoding. But what the theory of fault tolerance looks into is the more realistic scenario where the noise is present throughout. It's present in the encoding. It's also present in the idling qubits. It's present in the measurements. It's present in the state preparation. And now, how good are your error correcting codes and your error correction circuits in handling noise when all your gates, in fact, are faulty or noisy? This is joint work with my student Akshaya and my collaborator Hui Kun and her student at CQT Singapore. So, Akshay, do I have 5 more minutes?
Yeah, please go ahead, Prabha.
All right, okay, thanks. So yeah, so this is how I was leading up to this. So QEC assumes ideal gate operations, perfect preparations and measurements. So how effective really are error correcting protocols when you have faulty gates, preparations and measurements? So this was a question that of course people have asked much earlier, right? Soon after the theory of quantum error correction was developed, this was a natural question to ask, right? And the theory of quantum fault tolerance was developed, which allows for reliable computation even with noisy quantum states and faulty quantum gates, with a caveat that the noise in the system, and now noise includes everything, the decoherence of the qubits, the noise in the gates. So this noise has to be below a certain threshold value. So if that is guaranteed, then the theory of quantum fault tolerance allows for reliable computation. So that's what I'm going to talk about a little bit now. So what happens in a fault-tolerant computation? So the error correction, the success of at least these, the theory of error correction tells me that instead of looking at physical qubits, I must look at logical qubits. Now, if I start looking at logical qubits, then I'm looking at 3 qubits or 4 qubits in the place of 1. So I must naturally look at logical operations. I must look at encoded operations. So that is what this equation captures for me. I have a gate G, which acts on a single qubit system. But now I have a gate G bar. This must map to a logical gate, which is what is represented with this little bar on top, where this logical gate operation now acts on the code space. It acts on the 3 qubit space or the 4 qubit space or the 7 qubit space, right? And it acts on the logical qubits. Now, the key to a fault-tolerant scheme is that it must present a way to implement these logical gates, starting with physical gates, in such a way that the spread of errors is controlled. So what do I mean by that? So we'll come to a concrete example of this very shortly. So these encoded gate operations are often implemented by what are called gadgets. Okay, and I'll show you an example of some gadgets that we have built. And there are some technical terms like locations of faults and so on, but maybe we don't need to get into this detail. Suffice it to say that an encoded operation like this, what I've shown with this equation, does not comprise of a single physical gate, right? Because it's now a gate operation on 4 qubits or 5 qubits. So it's a gate operation on the logical space. So it's a composite object. It's a circuit in itself, which is made up of elementary gates. And I should now assume that any of these elementary gate locations can fail. Like in the example of the 3-qubit encoding, either of those C0s could fail. And you realize that if a C0 fails, it's a bit of a catastrophic fail because the C0 is an entangling gate. If the control has a fault, then that propagates down to the target. So I should now take into account all possible faults that occur in an encoding gadget or in a logical gate operation. And the way I do it is by actually counting the number of locations in which such faults can occur. Okay. So of course we stick to the IID assumption that it acts on individual qubits independently, etc. And the key challenge is to design gadgets in such a way as to minimize the propagation of errors due to faults within the same block. So what do I mean by propagation of errors is exactly what I was referring to with using something like a 2-qubit gate. That if I have a fault in the control, it propagates down to the target. And now what was a single faulty location may have become 2 fault locations. So one has to take this into account and somehow be able to detect and correct for these faults as you go along in the computation, so that you're always within the limit of the number of errors that your error correcting code can correct for. So this then leads to the idea of a fault tolerance threshold, which is a critical value of the error rate at which the fault tolerance protocol fails. And by failure, we mean that the unencoded qubit actually does better than this encoded qubit with the encoded circuit. Okay. So this was a sort of quick primer on fault tolerance, and now I'll just motivate our work in the next few minutes. So standard fault tolerance schemes focus on what are called Pauli noise, right? This is the same issue that I was mentioning with error correcting codes as well, that we assume that each location, now I'm not going to say each qubit, I'm going to say each location is affected by independent Pauli noise. And for such kind of models and specific error correcting codes, error thresholds have been worked out. These fault tolerance thresholds have been worked out. So for example, for the 7-qubit code, the fault tolerance threshold is of the order of 10 to the minus 4. What is this threshold? It's basically the probability of failure of a particular location or a particular gate or a particular qubit, right? So, and the way one arrives at this threshold is by computing the number of faulty locations which can lead to catastrophic errors. Okay. So the 7-qubit code, by the way, by itself is not fault tolerant. So if I have to make one of these error correction schemes fault tolerant, I have to add more qubits. In particular, in the 7-qubit code, it's the concatenated code, which means I have 49 qubits, which now correspond to a single logical qubit. And provided the single logical error rate is below this value, we have fault tolerant computation. Today, the best fault tolerance threshold numbers that we have, so obviously you see this 10 to the minus 4 is very low. It's a very low failure probability threshold for the kind of devices that we have today, where the lifetimes are of the order of 100 microseconds, right? So you can assume that these failure rates are obviously going to be much higher. So the search is on for fault tolerance schemes that will give us higher and higher thresholds, that will allow for higher and higher error thresholds. So some of the best error thresholds that we have today come from the so-called surface codes, and this is a term you've probably heard talks about this, which have hundreds of qubits, right? And for surface codes with depolarizing noise, we know that we can achieve thresholds of the order of 0.01, which is now much closer to realistic threshold values. However, this requires about 100 qubits for a single logical qubit. Okay. Now one can do something different and ask, can you achieve fault tolerance against specific noise models? Instead of looking at, again, general purpose Pauli noise, can I try to build fault tolerance schemes for specific noise models? This kind of effort has been done in the past, but there the specific noise that is assumed is again of the Pauli kind, like dephasing noise or bit flip noise. So our work looks at what is called noise adapted fault tolerance. And since I don't have much time, I'm maybe going to go ahead into our results basically. So we assume that the dominant noise process affecting the device is amplitude damping noise. And So I'm not going to get into the technicalities of these things. And what we show, basically using the 4-qubit code, so this maybe I should pause and show you what these circuits look like. So what I'm presenting out here is the complete set of fault-tolerant components that I need to build my 4-qubit error correcting code. Okay, and obviously you see that as the components start getting put together, this doesn't look very pretty. This looks pretty complicated. But what we can show is using the 4-qubit code, which is tailored for amplitude damping noise, and using a particular way of doing the error detection and error correction, we do achieve some kind of finite threshold. So long as your error rates are below that, we can actually achieve fault-tolerant computation, even in the presence of a non-Pauli noise model like amplitude damping noise. So there are some other interesting issues that crop up about the gates having a particular structure and so on, but maybe this is a little too much for this talk, so I will not get into this, but I'll just, yeah. Okay, so maybe I'll just talk a little bit about this figure and then I'll conclude. So what this figure shows is how one would implement a control Z operation, which, as you know, is a simple 2-qubit operation on the 4-qubit code. And this shows how you can do it fault tolerantly, where you're fault tolerant to amplitude damping noise. So the psi1 represents, for example, the control block. The psi2 represents the target block. And these are individual control Z gates between control and target. And this complete circuit has to be followed by an error correction circuit, both at the control and the target. And the output of this will be fault tolerant, which means that it can always correct and detect for single qubit damping errors. There is no catastrophic propagation of errors. And for a, so this is what I meant by a gadget. So this is a control Z gadget for 4-qubit code and amplitude damping noise. And using these kind of constructions, we show that so long as your threshold is of the failure of a single qubit gate is of this order, you can achieve fault tolerance against a non-Pauli model like amplitude damping noise. So for this is, as far as we know, the first time that we really have a characterization of a threshold for a non-Pauli noise model, which is generic to certain qubit architectures. Of course, this threshold number is fairly low, but that's because we have not really optimized these circuits. We have just built one set of fault-tolerant circuits for this noise model. So let me conclude with this. There are several technical points which I skimmed over, but maybe the first point is the takeaway point, that we have a universal fault-tolerant scheme tailored to amplitude damping noise using the 4-qubit code. And going forward, we'd like to optimize this further to see if we can jack up this error threshold to more reasonable levels. So thanks for listening, and I'm sorry I overshot, but I'm happy to take questions.
Thanks a lot, Prabha. This was wonderful. Questions from the audience? Yeah, Vyom, please go ahead with your question. And other people, please use the raise hand button.
Yeah, please go ahead. Yeah.
So what is the order of the threshold required for, say, general qubit architectures, for, say, superconducting qubits?
Yeah, see, this threshold is a function of, so let me just go back to where I had the threshold numbers earlier. So this threshold is a function of what noise you assume. So you're asking me experimentally, where are we in terms of the noise threshold, or you're asking me the theoretical estimates?
No, theoretically, so what
Yeah.
what
do we
number
require?
should we hope to achieve to, basically what we require?
So that is a function of what kind of noise you assume, because every theoretical estimate of a threshold assumes a particular noise, right? The most general thing to assume is what is called independent Pauli noise, which means you assume that every location can randomly get affected by one of X, Y, or Z, okay? And it also depends on the code that you consider. So This is the most general result as far as I know, which is for a concatenated 7-qubit code and independent Pauli noise, right? This is a threshold number that is required, that the failure probability for a given location or a given qubit should be of the order of 10 to the minus 4. But now if you're willing to use of the order of 100 qubits for a single logical qubit, then you can jack this up by 2 orders of magnitude and you get to 10 to the minus 2, right? So on the other hand, if you assume specific, much more specific noise model like dephasing noise, then you can simply use a 3-qubit code and get a very nice threshold of 10 to the minus 2. So this was the sort of result that motivated us to look into a specific non-Pauli noise model like amplitude damping, and again ask, using just the 4-qubit code, can you achieve fault tolerance and can you achieve a nice threshold? But these are the kind of numbers that we have today. Okay.
All right. Thank you.
Yeah.
Any other questions? Vyom, do you have another question? Okay, no, sorry. Vijay?
Yeah, hi. I just wanted to know if there are going to be more talks, I mean, for surface codes or beyond this.
Sorry, Vijay, are you asking the Quantox organizing committee?
I'm asking someone, I don't know. Is there a follow-up to this talk?
If you have follow-up questions, maybe you can email Prabha.
No,
but
not questions.
As of,
I mean, okay, so this was the only
Yeah,
talk that
sorry.
you guys organized?
So we have a series of talks on various topics. Last talks was on the surface codes, and I think you have attended that talk. Is that correct?
No, I did not actually.
Okay, so if you go to our YouTube channel, I think Shivita can help here. There is a talk on surface codes.
Okay.
So you can take a look and you can get back to us if there is any.
All right, okay. Thank you.
Thanks. Okay, other questions? Aman, please go ahead.
Yes, can you hear me?
Yeah.
Yeah, so I wanted to know that you have, assumed to use a noise model for a particular model. You simulate it or numerically extract the value, but there can be models in which there are poly and non-poly noises together also. So
Indeed.
anything about that?
Yeah, in fact, the most typical noise model is where you have both T1 and T2, right? And T1 being damping is non-Pauli and T2 being dephasing is actually Pauli. And I think that would be the holy grail in some sense, if one can actually find a way to address both these noise models for themselves rather than using general purpose codes. So one thought could be, if I can take something like a 4-qubit code which is tailored for amplitude damping and then concatenate it with something which is tailored for dephasing. However, such a concatenation has to be compatible at some level, and so far we don't yet know of a good case where these two have been compatible. We don't yet have good codes, maybe not yet identified good codes, where you can concatenate the 4-qubit code with another code which can correct for Pauli noise. I mean, that would be the ideal scenario, right? That if I know that the base architecture is predominantly of the damping type, then I do, at first level, I do the 4-qubit, and then on top of that, I do a general purpose code, or vice versa, right? Whichever is dominant at the physical level, I address that. So we don't yet have codes of that form, right? We only know of concatenations of Pauli codes, general purpose codes. We know of how to concatenate stabilizer codes, but we don't yet have an example of concatenating something like the 4-qubit with a stabilizer code. I hope that answers your question.
Any other questions from the
I
audience?
think Naveen has raised his hand. Hi,
Okay,
Naveen.
Naveen, please go ahead.
Yes. Yeah. Hi. Thanks. Thanks, Prabha. It was a very nice talk.
Thank you.
I'm trying to learn from some of this stuff myself. I had a question. So you, you said you've illustrated this amplitude damping noise as a specific noise model, which is not generic like poly. Now, what are the other types? Other examples of these noise models that people look at that are actually maybe relevant in practice? What other examples are there of specific noise other than the generic?
Yeah, so go beyond Pauli noise, you're saying. So is amplitude, yeah. So amplitude damping is, is one of the, like I said, the most ubiquitous such models. But there is, of course, a sort of generalization of this called the generalized amplitude damping noise, which also occurs in several physical systems, particularly in photonics systems, where this damping is more symmetric between 0 and 1. Or you can think of this as a higher temperature version of amplitude damping. There are other sorts of dissipation processes that happen in these, wherever you have, cavity QED kind of systems, or, sort of discrete level systems interacting with a continuous qubit. So photon loss, for example, that's not something that's easily modelable in terms of Pauli's. That also requires special classes of codes like permutation invariant codes or photon number based codes and so on. So these are the three that I can think of off the top of my head: amplitude damping, generalized amplitude damping, photon laws. At least these are the three that naturally arise in physical scenarios that we know of.
Great, thanks. Can I ask another question?
Sure. Yeah.
Yeah, like the you mentioned like the noise threshold, or the tolerance rather, that one builds, like for fault tolerant circuits. There's two specific examples that you gave was for the 7 qubit Steen code, I think.
Yeah.
When you with the concatenation up to 49 qubits, you're able to get a threshold of the order of 10 to the -4. Then there was the surface codes, which with 100 qubits. I'm not sure if it is referring to the same code now or not, but then now the threshold has gone up to 10 to the -2.
Exactly.
Let me just say, stick to the Steen code, 7 qubits. And if I ask whether, if I want to build a like threshold of, like, if I want to get a fault tolerant circuit with a higher threshold, let's say 10 to the -1, is there an understanding of how many qubits I would actually require?
What you're asking is if I go to higher levels of concatenation of the Steen code, do I get better?
Not really.
Threshold?
I mean, is there an understanding of how many qubits will I require? The trade-off between the number of qubits needed to get a certain order of level of fault tolerance, or let us even say the particular Steen.
Yeah. So the way these thresholds are actually arrived at is by plotting this. I don't have that figure in my slides, unfortunately. Is actually by plotting the physical error rate versus the logical error rate, right? And then you ask at which point do they all cross, right? And then you plot this for various degrees of concatenation of this code, and then you find that for this entire class of codes, which is this concatenated 7-qubit code, for example, you end up with a threshold of this number. Now, the surface codes, the way we get the threshold number is literally by brute force calculation. So if what you're asking is, do we have an understanding of how to go from something which is just 49 qubits to something which is 100 qubits, is there a way to sort of interpolate this and ask, is there a way that this changes, right? How the threshold changes as a function of the number of qubits. I don't think we have an understanding of this yet. Because like I said, the threshold numbers are specific to the code. They are specific to the noise model. Like in the case of the surface codes, the threshold numbers are specific to depolarizing noise. So it's not random Pauli noise. So that's why I say that the strongest result is for the concatenated code, which is random Pauli noise. And there you can simulate this. You can simulate the logical versus the physical error rate. You can ask where the crossing point is, and that becomes your threshold. But For something like the surface code. Yeah.
Sorry, isn't that then for a particular construction of the fault-tolerant circuit itself?
Yes, indeed it is. And I don't think, okay, as far as I know, we don't know if this is like an optimal way to construct fault-tolerant circuits for the 7-qubit code. So, yeah, see, with the 7-qubit code, actually, there is not much more you can do. And the reason I say this is because the main gadget that you use to compute the threshold is typically a 2-qubit gate. So it will be like the C0 gate. And if you recall the control Z picture I showed you, the picture for the C0 for the 7-qubit code is exactly similar. It has these transversal, it's a transversal C0, right? And the error correction circuit is also fairly simple because it just makes use of X syndromes and Z syndromes. The only sort of non-trivial part of the 7-qubit code construction is the ancilla, which has to be in a 7-qubit cat state, which means a 7-qubit entangled state, right? So that's probably the only non-trivial part of this construction. So I don't see how one can actually think about optimizing that any further. But for surface codes, I think that maybe there's much more optimization that is still possible, right? So because there are indeed smaller surface codes that people look at. So, okay, so maybe I should tell you. So there are, for example, the surface code is a class of codes, right? So to achieve something like 10 to the minus 2 or 10 to the minus 1, you go to 100 qubits. But you can look at, say, 15 qubit surface code. And there you know that the threshold actually is around 10 to the minus 4. Okay, so you actually reach something like your Steam code threshold if you bring down the number of qubits in a surface code. So yeah, maybe for surface codes we do, but these are all numerical interpolations. They're not really, it's not really like an analytical estimate of how this goes as a function of the number of qubits. I don't know if that was maybe an incomplete answer to your question.
I think, yeah, that's good. Good to come to where I can get. Yeah, that's good information for me. Thank you very much.
Yeah, yeah, there are recent papers that you can find which talk about smaller size surface codes and the kind of thresholds that you can get. But with surface codes, I don't know how optimized these circuits are, right? Whereas with something like 7-qubit code, it's very straightforward almost, like how to construct these fault-tolerant circuits. The challenge with what we were doing is that we don't have this Pauli structure. So actually coming up with fault-tolerant circuits for this kind of a noise model requires a lot more playing around, required more tricks, right? And here I think there is more scope for optimization because it's not so straightforward how to construct some of these error correction circuits for this.
Okay, thank you very much.
Okay, thanks a lot, Prabha, for
Sure.
patiently answering everybody's questions. So let's thank Prabha again. Please use the applause button for thanking Prabha.
Thank you.
Yeah.
Thank you for having me here, and it was good to interact with folks here, and hope to visit you all in person sometime.
Yeah. Great. Thanks, Prabha. Okay.
Thank you.
Okay.
Yeah. See you all. Bye.